Okay, good afternoon, everyone. So let's start today's session. First, we'll start with some revision so that if others are also joining. Okay, so this is the sixth session for Solid State Physics NPTEL course. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am teaching assistant uh, Mrinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. As you know, these sessions we have every Saturday, 3 to 5 p.m., where we discuss that week's topics that were covered and then do some problems similar to the assignment problems you get so that it will help you in solving your weekly assignments. Okay, so first let's have a small revision of like what were the things that were covered last week. Yeah, first these are the recommended books for this course. And as now last week we were discussing about X-ray diffraction. So this book by B.D. Kaliti, Elements of X-ray Diffraction, this is a very good book with basic conceptual things there very clearly. So you can refer that. And yeah, now moving to what we had discussed last time. So earlier when we were discussing about lattice in real space, like when we deal with objects that we can see around us, when we talk about atoms and matters, what they are made up of, then we are talking about an abstract concept of lattice, and when basis, that is group of atom, is associated with those lattice points, then we get what we know as crystals. And then we had seen we have different type of crystals, its classification in 3D, that we have 7 type of crystal structure and then 14 Bravais lattices depending on the position of atoms on those lattice points. So this was we were discussing in real space. Then we had switched to another space that we know as reciprocal space and had seen how we can get translation vector from real space to the reciprocal vector in reciprocal space, what is the relation between them, and like the relation is usually, if we don't bother about the what constant, the magnitude, usually the a1 star, a2 star, these are the three reciprocal vectors in reciprocal space. And the formula is either sometime we keep this 2 pi or sometime not, and this is the formula where a2 and a3 are translation vectors of real space or lattice vectors of real space. So if we know the lattice vectors in real space, we can get the reciprocal vectors in reciprocal space. This we had discussed. And then we had discussed about reciprocal vector, what its properties are, and how it's also we had discussed about Ewald sphere and how we can get in reciprocal space also how we can get Bragg's law using Ewald sphere. Then after this we were discussing that when we have a simple cubic crystal in real space, then we how we take its a1, a2, a3 vectors, and then when we calculate the reciprocal lattice vectors a1 star, a2 star, a3 star for reciprocal space, then what these vectors tell us about the kind of crystal structure here. So we had seen simple cubic crystal in real space still remains simple cubic crystal in reciprocal space, whereas if we have FCC crystal, then it will become BCC, and if we have a BCC crystal in real space, then it will become FCC in reciprocal space. So we had like understood how this can be calculated. So this was all about reciprocal space and reciprocal vectors that we had majorly discussed last time. So this time we are going to move now from these lattice and vectors in crystal structure to electrical properties of matter. But before that, still a small thing we would like to discuss, and that would be on something on Brillouin zone and intensity, like XRD. So first, let's discuss Brillouin zone. So Brillouin zones, how do we get them, and what are their significance? So a detail with lot of derivation is already there in the lecture. So here I'll only brush up these things or only touch the part which Whipping may not have been told about in those lectures. So Brillouin zone, how we get? So Brillouin zone is a concept that we talk about when we are in reciprocal space. So in reciprocal lattice, when we draw our reciprocal lattice points, and with one reciprocal lattice point, first, how to get this? Let's first see how we get a Brillouin zone. So this is a reciprocal lattice, all this, and then let me draw one more. What we do is we take one point and then we connect it with its nearest lattice point. So for this, the nearest will be, let's say if this distance is A, then all at the distance A will be the nearest lattice point. So from this, first we connect these, all the nearest. This, if this is at the distance A, then this is diagonally, so it will be root 2 times A. So it's not nearest, it would be second nearest. So as I said, first we will be connecting the nearest one. When we connect this, after that we draw perpendicular bisector. Perpendicular bisector means in the middle, the line will be cutting this segment in the middle and it will be perpendicular to it. Okay, so it has to be in the middle and it has to be perpendicular. So something like this, not like this or anything else. Okay, so at the center we have to draw perpendicular bisector. Then for this segment also we have to draw a perpendicular bisector. The length does not matter right now, we'll see. Then we have to draw perpendicular bisector for this joining also, and this as well. Now these four perpendicular bisectors that I have drawn, let's say this is first, this is second, this is third, this is fourth. These are the perpendicular bisectors I have joined, and they intersect, they touch each other, intersect each other at these points. So this area, because right now this screen is 2D, so maybe we can say we are discussing for 2D, but this is applicable for 3D as well, where I'll be doing this in all three directions outside the plane also. So right now just taking this as 2D, this area occupied by these four blue segments or four blue walls is the area that would be called first Brillouin zone. Okay, and then this is first. Then how we get second Brillouin zone, because first Brillouin zone is not the only Brillouin zone. After this comes second Brillouin zone. How we get that? So first, for getting first Brillouin zone, we had connected this one lattice point with its nearest neighbors. Now we'll connect the second nearest neighbor. Like I said, this was at distance A. If say these were at distance A in both directions, okay, that means this diagonal one will be root 2A. We know, right? When we have a cube and all the edges are A, then the face diagonal is root 2A. So now we have to connect the second nearest. Again, let me change the color. Okay. Now I'll join with this center its second nearest neighbor, which will be these and this. And similarly, this is also second nearest neighbor. This is also second nearest neighbor. Okay. So I've connected these four second nearest. Now no other are left. Now again the same procedure we have to do. We have to draw perpendicular bisector. Let me know if this yellow is not visible. I hope it is. So now I have to draw perpendicular bisector for this. So in the middle it will go and perpendicular. This also in the middle it will go and perpendicular. Same thing here. To this green joinings I am drawing this perpendicular bisector. Okay. So now, oh sorry, not this one. Maybe this yellow color is little hard to see. Okay, it's okay, anyways. Oh. So joining this green segment, we have perpendicular bisector can be drawn here. Okay. Now you see these perpendicular bisectors will be like this. Okay. Now this area, actually because the spacing between these lattice points is not constant because I have drawn roughly. Otherwise, if we draw it properly using a scaler or scale or ruler or something, then we will get accurately. So because these lattice points were all at constant distance, so the first Brillouin zone here actually is also a square, and the second one, like here, this portion will also be inside, like this area, because it's drawn, that's why it looks like this. But okay, so the area occupied, area enclosed by these blue walls, as I said, it's first Brillouin zone. Now the area enclosed by this yellow four walls, but outside this blue. So inside this yellow segments, but outside this blue segment would be our second Brillouin zone. So this space and this all and this. Okay, so inside this blue one, all this blue will be first Brillouin zone. I have not shaded, but just whatever is inside this blue one is first Brillouin zone, and whatever is inside this yellow segments but outside this first Brillouin zone is our second Brillouin zone. So these are second Brillouin zones. And then to get what will be the third Brillouin zone, again you have to look for this center lattice, reciprocal lattice point, who are its third nearest neighbor. Maybe this. So there when you will do perpendicular bisector again, okay, maybe this will be a third Brillouin zone. So that way we can construct Brillouin zones. So I just wanted to tell you, because I think in lecture maybe only one Brillouin zone drawing was told. So I just wanted to tell you one this thing, that there are many orders of Brillouin zones, and this is the way to draw them. I hope this is clear. That for first Brillouin zone, we connect the immediate neighbor. Then for second, we go for the second nearest lattice point, and the so on. Okay, so depending on what kind of lattice arrangement is there, the shape of Brillouin zone will change. Okay, so Brillouin zone, named after scientists who gave this concept, is a defined primitive cell in reciprocal space. So here, these walls that we are calling, which are enclosing the Brillouin zone, these walls are correspond to crystal plane in real space. Okay, this is reciprocal lattice point, and these walls that we constructed, these correspond to crystal planes in real space. Right, boundaries of this cell are given by crystal planes related to points in the reciprocal lattice. The first Brillouin zone is the locus of point, means all the points in the reciprocal space. Yeah, so what the Brillouin zone tells us, like for here for the first Brillouin zone, all the points, whatever point will be inside this first Brillouin zone, that point will be nearest to this lattice point than it would be to any other. You can see if there is a point, any point here, or any point just on the right of this plane, then it would be nearest to this center one and not to any other lattice point here. This is also a way to define Brillouin zone, that the first Brillouin zone is the locus of points in reciprocal space that are closer to the origin of the reciprocal lattice. This center one we are calling origin of reciprocal lattice than they are to any other reciprocal lattice point. This is also how we define Brillouin zone. Okay, so this is about how we define Brillouin zone. And then, yeah, depending on what kind of arrangement of lattice points we had, if we had something like this square lattice where all the lattice points are at constant distance in x and y direction, then their Brillouin zone will also be square. Whereas if my reciprocal lattice points are arranged in hexagonal, right, you can see they are in hexagonal arrangement lattice points, then the procedure will still be same, because I'll take my origin or center of reciprocal lattice, and then I'll connect all the first nearest neighbors, and I have to take this perpendicular bisectors, and these perpendicular bisectors when I'll get a hexagon like this. First Brillouin zone this will be. So depending on what arrangement my reciprocal lattice has, my Brillouin zone shape will also change. So yeah, be careful. And if I have rectangular arrangement, so it will be definitely different than a square lattice. Okay. So importance of Brillouin zone, maybe it's difficult to understand right now, because again this is a concept in reciprocal space. But Brillouin zones is a very useful concept when we are trying to study or understand periodic medium. Okay, there we talk about Bloch's theorem and other things. Maybe this we will encounter when we'll talk about acoustic waves or matter waves or something. That time we'll get to see this. But so this was just about getting some idea about Brillouin zone and about its construction. Okay, so after Brillouin zone, the next thing that we should have little discussion on would be intensity of XRD peaks. Sorry. So we had earlier discussed about what is the use of XRD experiment, how we get XRD waves generated, and why we use XRD waves only for understanding matters and unit cells. Then we had discussed we have different type of powder diffraction, Laurent's diffraction, and what is constant there and what we can change to get the peaks. But so when we do this measurement, I think we had discussed this also. Yeah, I had told you guys that. Okay, where is my pen? Okay, yeah. that we when we get the data, we get intensity versus 2 theta, and I'd also explained why we take 2 theta on x-axis and not only theta. So when we get the graph, we get peaks corresponding to different 2 theta values. Okay, so depending on what type of material, atom, crystal, whatever samples XRD experiment we are performing on, this intensity of these peaks and of course the position of these peaks, they differ. So position, it depends where for that particular material. We know for XRD peak to happen, it should the incident XRDs on the crystal planes should satisfy this Bragg's condition. And when, depending on what is the interplanar spacing of those crystal planes, we get the peak at that particular 2 theta here. But not the peaks, whatever at 2 theta value we are seeing the peaks. The peaks don't have same height or same intensity or the same area under the. So usually intensity of peak, when we say, we mean the area under that peak, not just, it doesn't just mean the height. Okay, because there is lot of lot of physics behind why the peak is broad or why the peak's height is more or less. So it's just not random. We are not only always only this is sufficient to know that what is the 2 theta value, but we also consider about the height, about the area under it, about what is the width of the peak. All these because tells us some crucial information about our sample. But here for our uh, discussion, we don't need to bother about more in detail, but you will find all these things in the BD Kaliti book on XRD. That's a very thick, big volume book. You can find a lot of things related to XRD. But here we'll just talk about how the intensity of XRD peaks vary, what parameters they depend on. Okay, so XRD peak intensity, as I told, refers to the area under the peak and not the peak height. The intensity of a diffracted peak, the XRD peak we call, or diffracted peak we call, it's same, is determined by following factors: structure factor, multiplicity of the crystal plane, Lorentz and polarization factor, temperature factor. There's not only these four restricted, there are other some parameters which also tend to influence or affect the XRD peaks. But the important one, the most important one that we need to be careful of is the structure factor and the multiplicity of the crystal planes. The other, especially this temperature factor, is usually we don't worry about much. But yeah, of course, if the temperature difference is too much, then we'll see what may happen. But usually we don't bother about the other factors. What we need to pay more heed is the structure factor, how it influences the intensity of the diffraction peaks, and the multiplicity, how it causes the intensity of the peaks to increase or decrease. Okay, so moving on to the first factor, which is structure factor. So structure factor, the formula is given by this. Structure factor depends on the HKL value because we are talking about that particular lattice plane. The structure factor is calculated for that plane, whatever it could be, 100 plane, 110 plane, or 111 plane, or any plane we are talking about. So structure factor incorporates information about atomic locations within the crystal and determines if their collective interference will give us a diffracted peak or not. Means whatever diffracted XRD peaks we are getting, will they interfere and give us a resultant in on when we our detector will detect it or not. So this is the basic formula of structure factor. Here, this is just summation. This F is form factor. We'll see what this is. then this is just e to the power minus 2 pi hx ky lz, where x, y, z are coordinates of our atom, any atom. Like if I consider this as 0, 0, 0, we can take any, because all are identical, right? That's why in when we were talking about symmetry, that time also we had seen that this like this unit cell has four-fold symmetry. Even if I turn this atom by 90 degree, I mean if I rotate this unit cell by 90 degree, this will come here, this will come here, all will replace each other, and the atom will look, if all the atoms are same, all the atoms will look the same. I mean the unit crystal will look same because this is symmetric, and there is nothing different if you take this as origin or this as origin or this as origin. So in that way, here I'm saying we can take any point as origin, and when we take, let's say, this as origin, then this, the position of this body centered will become half, half, half. Okay, and these will be like 1, 0, 0, or like that. So when we consider these positions of atom, that is what we mean by xyz, and hkl is corresponding to that plane. If like say I'm talking about the top plane, then it will be say like maybe 0, 0, 1. If I'm considering this as x-axis, this is y-axis, and this is z-axis. So these are the things. Then form factor, what we mean by form factor is the ratio of amplitude. Form factor is defined as ratio of amplitude of X-ray which is scattered by the atom on our crystal plane. So I told you, right, sometimes we talk that the X-ray is incident on the all the atoms, like it's coming and their atomic arrangement on the plane, and they are diffracted from this. Sometimes we also say the X-ray is reflected, because then we consider not the atoms but the plane on which these atoms lie. So it's like reflection from mirror. That's why we use the word reflection. Or otherwise, when we want to focus on the atoms, then we say it's diffracted from the atom on that plane. So there are different way of saying the same thing for XRD here. So when XRD is incident on these atoms, then they are scattered by the atoms and they go out as diffracted X-rays. So they are scattered by atom as a whole, or if we go in detail, then we know there is positive core in atom and there are electrons revolving around atom. So we are just saying that it's getting scattered by atom, but actually it is interacting with every, or electron, depends. Okay, so it's actually interacting with the electrons of atom. So there, this is just different way of saying. Either we say it's interacting, XRD is interacting and reflecting from the plane, or we say it's diffracting from the atom, or we actually it's electron absorbs and releases the XRD. This is what happens. So this form factor we define as amplitude of X-ray scattered by atom, and in denominator we have amplitude of X-ray diffracted by electron. Okay, so amplitude of X-ray diffracted by electron will be one thing, and amplitude of X-ray diffracted by atom. Now by atom we means lot of valence electrons would be there, or lot of electrons will be there in atom as the atomic number goes up, right? So the form factor increases with increase in atomic number, because the higher we'll go to, as we'll go to higher atomic number of electrons will increase. So amplitude scattered by single electron, this value will be same, but amplitude of X-ray scattered by whole atom, because there will be more electrons, so scattering value will be more. So this form factor, it increases with increase in atomic number. Like if we are talking about hydrogen atom, this form factor will be less, because in hydrogen we have only one electron, right? So this will be a small value. In fact, this you can understand could be 1. And if you are talking about a copper atom, then there will be more number of electrons, so form factor will be higher for this. So this is one thing about form factor, and this is how we calculate scattering factor. We need form factor for it, and the remaining thing I told you, this is how we take position and then HKL value. So what interesting thing happens when we talk about structure factor is that when we calculate structure factor based on this formula, and there's a little derivation, we don't need to get into it, but what information we get from this is that depending on what is the arrangement of atoms, we get some rules for these HKL, which are the Miller indices for our plane, right? So we get some rules on these HKL which tell us that which corresponding to which plane we can get the diffraction peak for that particular kind of unit crystal. For example, if I have a BCC crystal unit like this, which has atoms on the corners and one in the body centered, then after calculating the structure factor and taking the position of these atoms in this formula, we get, after a small derivation, we get to see that if for BCC we are saying that if my HKL, whatever plane we are choosing, if its HKL values, I take the sum, and if it comes out to be, if it comes out to be even, then that plane will diffract the peak and we'll see that peak. If the sum of those HKL values is not even but odd, then whatever X-ray will be diffracted, they will do destructive interference and we won't be able to see those peaks. So this is very important information we get from this structure factor formula about, depending on again the crystal, unit crystal we are talking about, because this helps us identify what kind of crystal we have. So that's what I'm telling. XRD doesn't just gives us the 2 theta position using which we can find out interplanar spacing. This is not the only information we get. Depending on peaks, depending on width of peak, depending on what is the HKL values we are getting for these peaks, we can find out if this is SCC, BCC or FCC or something else. So there are a lot of experimental informations we get from this XRD experiment. That's why it's very popular and very basic. Like first, whenever we prepare any sample or something, first we go for the structural characterization using X-ray diffraction. Okay, so like here I have shown that if I'll calculate structural factor for 100 plane, it will be 0 because H is 1, here H is 1, K is 0, L is 0. So total sum will be 1, which is odd. Odd means it's odd integer. So because it's odd integer, so that means the X-ray diffracted from 100 plane, I'm talking about BCC only here. This is for BCC. This is not in general. This is only for BCC because this XYZ is also there in this formula, and this first we'll put the position of atoms of BCC here, then only we'll be able to get these conditions. So this presently we are talking about BCC. For BCC, 100 plane will not see, 111 plane will not see, 210 plane will not see. But 110, why 110? Because here H is 1, K is 1, L is 0. So when we'll add these three, we'll get 2, which is an even integer. So X-ray diffracted from 110 plane, we will be able to see that in case of BCC. Whereas when we talk about simple cubic structure, so all planes are allowed for SCC and there is no such rule. All planes are allowed. Whereas when we talk about FCC, okay, so this is a picture where we can see sodium element, it has BCC structure. So you can see only 110, 200, 211, 220. This is 2 theta, versus intensity graph. So if we'll take XRD of sodium sample, then we'll get peaks at for corresponding to 110 plane. Usually we denote it like this because we denote planes, right? So we will get corresponding to 110 plane, 200 plane, 211 plane, 220 plane, and if we take measurement up to higher 2 theta values, we will see more. But and what we need to see is that HKL here also, when we'll add H plus K plus L on all for all these values, it will be even integer, and that's why for a BCC we see these peaks. We don't see 111, we don't see 100, we don't see 300 because they all will give H plus K plus L. So it's not something we have made out of ourselves or something. We have a formula we came up for, and when we put the value we get these rules. Okay. And here we have CSCl's X-ray data. Now CSCl, cesium chloride, it has SCC structure. So as I said, SCC doesn't have any such rule. So here when we take its data and plot 2 theta versus intensity of the diffraction, then we see all possible values of HKL. HKL here, the sum will be odd, the sum here will be even, the sum here again is odd, but all the values all are present. Okay. Now, yeah, I was telling there is again some rule for FCC, and that rule is, if I get some space, okay. The rule for FCC crystals is the rule in case of FCC, where again the position, the structure factor formula will remain same, but the position of atoms will be, now if I take this as origin, so one will be 0, 0, 0. Another positions will be on the faces, because the 0, 0, 0 covers all the corner one. Now I have to see the position of these 6 atoms. So I'll take the position, it will be from the origin, it will be half this side, half this side. Yeah. So half, 0. The second one will be half, 0, half. Similar way I'll write for all the atoms, and then when I put that in structure factor, so I'll get some rule, and that rule for FCC I'll tell you is that if HKL, here we don't take sum, but what we see is that HKL, these values, if they are all even, okay, or they are all odd, in this case our structure factor will be non-zero and we will get diffraction peaks. But if HKL, they are mixing of odd and even values, then structure factor will be 0 and we will not get any diffracted peaks. Means if I have 1, 0, 0 peaks, we know zeros are even and 1 is odd, so we will not get diffraction peak for a FCC crystal from 100 plane. Okay, because 100 plane is there, of course. If it's a cubic, this is the 100 plane, right? 100 plane is there, but we will not be able to see diffracted peaks from this, and if the atom position is on the face. And similarly, if I have 111, then all HKL are odd, so we will see this plane. We will see 2, 2, 2 plane, or we will see 1, 1, 3, because all are odd. But intermixing, if HKL have even and odd mixed, then we will not see any diffraction peak. So these are some rules which help us when we get XRD peaks. It helps us identify what kind of crystal structure it could be. So this was other information, but basically what we were discussing, that the structure factor that we calculate, that tells that affects the intensity of peak, because depending on the structure factor we may completely what have zero intensity for that particular plane, or we can have some intensity. So this is one of the parameter that affects the XRD peak. Next important factor is multiplicity factor. What multiplicity factor means is that if I am taking a cubic crystal and I'm talking about diffraction, X-ray diffraction from say 100 plane, okay, then we know 100 plane, if it's a cubic crystal, then it will have a family of how we denote family of planes using this. Yeah, this is the way. When we write like this means all 100, 1 bar 00 or 010, all those planes. Like here we can see, because it's a cubic system, it could be FCC, SCC, BCC, but if it's cubic, it is symmetric, and that means this 001, 100, 010, and all these will be like identical. In that case, the X-ray can diffract from here, it can also diffract from here or here, okay, and we'll get diffracted beams from all the 001, 100, 010, they will all be giving diffraction at the same 2 theta values, because their interplanar spacing is same, and from our Bragg's law we know if interplanar spacing is same, then because other things are fixed, so theta uh, diffracted peak we'll get on the same theta position. So here the intensity of peak is like 6 times from this 001 plane family. It will be 6 times. Whereas if we are talking about the X-ray diffraction from 110 peak, okay, this is our 110 peak. Then 110 family plane has 12 identical planes. These 110, 1 bar 10, 1 bar 1, this is same, it should be something else, 1 bar 0, 1 bar 1 bar 0, and so on. That means that intensity at that particular, for that particular 110 plane, at whatever theta value it is going to appear, it will be 12 times intense. Okay, so for many crystal structures, particularly those with simple unit cells, there will be more than one plane in the system with the same crystallography. In other words, if you look at the crystal from a different direction, it will look the same. This is what I'm saying. Because it's symmetric and it's a cubic unit cell, it's symmetric. This plane, all these 6 faces are same. So for XRD also, all these planes are same. So whatever will be diffracted from these planes will appear at the same theta value, and we'll get a intense peak at that position. But see, like I said, these 100 will be 6 times intensity. This 110 will have 12 times intensity. Whereas if you see 111 peak, okay, which is, we know 111, okay, it intercepts at 1 on the x-axis, y-axis, and z-axis. If you are talking about this plane, and we are talking again about a cubic crystal, then we can have its different variation will be 1 bar, 1 bar, 1 bar, 1 bar, 1 bar, and 1 bar, 1 bar. Then what is it? 1 bar, 1 bar, 1. Only this, and it 1 bar, 1 bar, 1. I think only these 5, 6, 7 are possible. So the peak diffracted from these planes will be less intense than compared to these 100 and 110. So I hope this is clear. This is how multiplicity factor. This is, I hope the meaning is also clear, because if I'm considering diffraction from 100 plane of families, then my peak will be more intense because there are more 100 plane in a way. Because here 100 plane, 010 all are identical. So there are more planes to do that same diffraction. So intensity will be more for that peak. Whereas if I have a plane, I'm talking about a plane like 111, then there are less number of 111 planes. So the intensity of peak corresponding to this plane will be less intense. And this is what is given here. So this is how multiplicity factor also influences the intensity of peak. Like maybe like here you can see 110 plane, although this is for BCC, but just like I'm telling, this is more intense, this is less. So this is also one factor that here like you can see 100, it's less intense because there are like 6 planes, and 110 has 12 identical planes. 111 has even less, like about 6 identical planes. So this is also one reason why it keeps the intensity varies for different planes. So this was another important factor. The next factor is, usually we don't need to bother much. These are Lorentz and polarization factor and temperature factor. So Lorentz and polarization factor, they refer to the summation. This is the formula. Okay, this here is actually intensity of peak, which is proportional to, this is the formula. So here you can see it depends on the 2 theta. So according to Lorentz polarization factor, the thing is they include geometric considerations such that number of crystals oriented to satisfy Bragg's law are largest at small angles, and that's why the intensity of peaks is more at the small angle. This is a lot of concept, maybe not that important, we don't need to worry much, but as you can see, at smaller angles the intensity of peak is more than at the smaller angle. Like here 100 is here more intense than 200. 110 is more intense than 220. That happens because of this factor, where we consider that there are more number of diffraction planes at smaller angles. Okay. Another thing is temperature factor. So when we give temperature or when we increase temperature of any sample or material, what happens is the atoms take that energy and starts vibrating vigorously. Because of that, what happens, if I have a plane and my atoms are vibrating a lot, then maybe whatever X-ray is diffracted from them, because they are continuously moving, so the diffracted X-ray may not be able to satisfy 2D sine theta Bragg's condition, and thus the diffracted peak may not be observed. But if it is at low temperature or room temperature, depending on what kind of atom it is, and it's not vibrating much, then it is constant at its position and the X-ray is coming, getting scattered, and depending on other factors that we discussed, it may or may not give us the peak. But this is not usually that big of concern in normal scenario, but this is also a factor that does slightly has its influence on XRD peak intensity. Okay, but yeah, so it is usually not largest contributor. It does not affect that significantly or hugely about the peak intensity, but these are also some factors. And then there are lot of many experimental, when we have experimental condition, when we are taking or performing that experiment, that time what different factors can influence how much sample we have taken, if the position of XRD and the sample is correct or not. So there are a lot of other factors, but those are different, external we can say. But here these multiplicity factor and structure factor, they are the characteristics of the material. So it does not depend, these factors are not external factors. They are very much the property of that sample we are talking about. Okay, so these were the things about intensity of exciting peaks. So after discussing about these crystal structures and these things, because this is one part of matter, whereas in this course we are talking about solid state physics, and we had started how we get matter, what kind of matter are there. There are like five, out of which three are very common, and then plasma. So we were discussing those things. Then we started discussing what are the building block of these matter. Then we came to crystal, which is lattice plus basis. So these were one structural aspect. Till now we were discussing structural aspect of a solid state or any kind of matter. Now further, the discussion this week, the lecture were based on electrical properties of matter. So first we started with structural properties. We discussed them, understood them. Now we'll move on to discussing electrical properties of matter. That in solids, what different electrical properties we study about, we investigate about, and what are the reasons behind them. So there are different models again. So this is done. So next is electrical properties of solids. So electrical properties, as I think thoroughly has been discussed in the lectures, we'll just go briefly. So first, the thing was, in solids, we have some materials. When we are talking about electrical properties, because in different categories we have different categorization. If I talk about a magnet, then I have some ferromagnet, diamagnet, paramagnet. But here we are talking about electrical property of solids. Then our categorization is, it has three categories. One is conducting material, which we call conductor. Then we have insulating, and the materials are called insulators. Or in general, actually, because when we say conductor, we mean it conducts, but not every material has same conductivity. They have different range. And insulator, same way, it's not like they all completely insulate. Some materials insulation is less. If you apply more current through it, if you apply more voltage, then it may start, after some magnitude, it may start conducting. Some leakage may happen. Like we see the example, air. We know air is insulator, right? But when we see sky, thundering happens, right? Thunderstorm, and there is lightning. Sorry, not thundering. We call it lightning, right? So what happens is, air, so much like kind of voltage situation happens around the air, that ultimately air starts conducting, and that's why we see that lightning. Like the charge is able to travel from cloud to earth. Although the air is insulating, but still this happens, and it strikes the tree or houses or something. Why this happens? Because there's so much uh, voltage difference that air starts, like, it breaks down, air's insulation breaks down and starts conducting. This charge, air gets, what we say, polarized, charge separation happens. So similar way, different objects we see around, their insulation, which we know as their insulation is inverse of conductivity. So that is given by resistivity or 1 over conductivity. So that depends on the material. And then we have semiconductor, which we know falls in between the conductor and insulator. So conductor, their band gap is very small or maybe overlapping. So they have conduction band, right, and valence band. For conductor, they are overlapping or very small differences there, so that electron can easily jump to conduction band and conduction can happen for that material. Whereas when we talk about insulator, we say that the gap between conduction band and valence band is huge. The energy gap is large, so electron is not able to cross this energy gap, and then when we apply voltage across this then it may cross or may not cross. Semiconductor, the energy gap is very small in between these two. So this is, we talk about electrical property of solids. Now further the discussion was on metals. What are the different properties of metals we see and what is the reason behind it. Then there were a lot of models discussed, that we have free electron model where we treat electrons in a material. We know we have ions, and then in metals what happens, why its conductivity is so high, because electrons, we have positive core of course, and the valence electron is so free, loosely bound, that we can actually imagine that the electron is freely moving all over the material. Of course, it cannot go out. It is just moving inside everywhere, and that's why whenever we connect a voltage source, the electron starts immediately. It starts moving because it's very loosely bound. So this is picture which is similar to whenever we discuss about gas. Gaseous particles are very weakly, they are not at all interacting with each other, which we had seen in case of solids, that the atoms are very closely bound and that's why they are rigid and not moving, whereas in liquid they are loosely bound, so they start moving. But when we talk about gas, there is kind of no interaction between the gaseous particles. The similar way the analogy is taken for electrons in metal material, and similar whatever theory and model was applied on gas and we had found out some formula, the same is applied on metals, and we find several properties like the mean free path, relaxation value. Then these all derivations were done, so we don't need to repeat it, but we had found out current density value, which is current per unit area flowing in the material, which is given by number density of number of electrons there, then velocity of those electrons, which we call drift velocity, and then the value of charge. So number of electrons, their drift velocity, and the charge on the electron, product of these three values gives us the current density of that, for that material. Then we had seen, it was also derived that how we get this relation, which is a vector form of Ohm's law. Because in scalar form we say V is equal to IR, means this I is proportional to V. This is scalar form of Ohm's law, and this is vector form of Ohm's law. This derivation also was discussed in the lecture, so we don't need to repeat it. We'll straightforward, we'll go to discussing assignment problems now. One more thing was the derivation on density of states. So so the concept of density of states, again this is very important stuff, but first here we will just focus on what it means. And there was simple derivation done in the lecture this week also. And density of states, it means number of allowed states or allowed electron positions per volume per unit energy. Like for energy interval, say E plus delta E is some energy range. In that energy range, when we talk about number of allowed electron states per volume per unit energy range, that is what we mean by density of states. Okay, and when we derive density of states for 3D material, we see for 3D the density of state for 3D, it's proportional to square root of the energy of that system, and the graph for this will look like density of state and E. Because it's proportional to square root of E, it will look something like this. Okay. For 2D, when we calculate this, the density of state is independent of, it doesn't depend on E, and thus the graph looks like this. Density of state. When we talk about 1D, density of state depends like e to the power minus half, and graphical representation will be like this, exponential decrease kind of. So like this better, not this, this. Here x-axis is this, y-axis is density of state. This is how it depends for 1D. And when we talk about 0D, that is like a point, then the graph is like a spike. How? Because for 0 dimension density of state value, it is a delta function, right? So that's why at that particular point it is there and nowhere else. Now let's move forward and let's focus on doing some assignment problems depending on these electrical properties of matter. So I think we have sufficient time for this now. So first question, let's do. A copper wire of 1 millimeter diameter carries a current of 5 milliampere. So we have a copper wire of diameter 1 millimeter and 1 millimeter and a current of 5 milliampere is flowing through it. Calculate average drift velocity. Average drift velocity of free electrons. So we are talking about copper metal, so we consider electrons as free electrons, like like the particles in gas. Copper is monovalent, means one atom contributes one electron, and crystallizes in FCC structure. We know FCC very well, with a lattice parameter of 3.61 angstrom. Okay, so to calculate drift velocity, when we have this, we know current density is this, right? We need number of electrons. We know charge of electron. Charge of electron value is 1.6 times 10 to the power minus 19 coulomb. So drift velocity we need to calculate. Current we know. Okay. This current density is what? Current density is current per unit area. Area we know because the wire's cross section we can calculate since we know the diameter. So this J we know, E we know, number of electrons we need to see, and drift velocity we will calculate, right? Drift velocity will be J over NE. But we need to know this number of electrons in this wire. So for that, since copper is monovalent, means one atom gives only one electron, and it's a FCC structure. Now we know that number of electrons per unit volume, this is number density, right? No, number of electrons per unit volume. So we know number of electrons. So FCC has, we know FCC has atoms on the corners and on the 6 faces. And the total number of atoms we have done many times, that all the corner atom contributes 1/8, and we have 8 atoms, means total 1, and we have 6 atoms on 6 faces, all contributing half. So half times 6 means 3. So in total we have 4 atoms in a FCC. We have 4 atoms. Okay. So number density means number of atoms per unit volume will be 4. And what will be the volume here? Number of atom is 4. And volume of this unit cell will be A cube, because it's cubic. And A is 3.61 angstrom. Okay. And everything is in SI unit. Okay. So that means number density will be 4 divided by 3.61 into 10 to the power minus 10, because 1 angstrom is 10 to the power minus 10 meters. Okay, and A cube means cube of this. And when we do this calculation, maybe we can directly put in formula. Let's move for the next step. So, or let me calculate this. So 4 divided by 3.61 means 1.108, and this will be 10 to the power minus 30. It will go up and it will be 10 to the power 30. This is number of electrons per unit volume. So 10 to the power 30 per meter cube. This is, oh sorry, I did mistake. This is cube. I missed to do this. Okay, let me calculate this again. So this n, which is 4 by volume, this will be 4. Let me calculate this cube first. 3.61. Its cube will be 47 point something. So when I will take 4 divided by, it will be, n will be 0.085 times 10 to the power 30 electrons per unit volume in per unit meter cube. If I will write it as this, then it will be 10 to the power 28 electrons per meter cube. Okay, this we calculated charge density. After that comes current density, right? I told you we can calculate, since current density is current per unit area, and area will be pi r square because it's a wire, and wire means it's like a cylinder, and current is flowing, like charge is moving here, so the area is this cross section area. We call it cross section area because when we cut a wire and we see this is called cross section. This cross section area is a circle, so the area will be pi r square, and we know the diameter. So we know diameter is 1 mm. That means radius will be this d by 2. Okay, that is 1 by 2 means 0.5 mm. And so current density will be, which is I by A. The current is 5 milliampere. Current is 5 milliampere, means 5 times 10 to the power minus 3 ampere divided by the area. Area will be pi r square, 0.5 millimeter square. Now because everything is in SI units, so I will convert this millimeter into meter. Then this will be pi and this square will be 0.25. And millimeter to meter, when I convert, it will be 10 to the power minus 6 meter square. When I put this value here, 0.25 times pi times 10 to the power minus 6 meter square, and I do this, then I will be left with 1 over pi so the 3.1 0.5 just a minute, 5 divided by, oh, I have 1 over 0.5 also, so 3.1847 divided by 0.05, and these exponents will be 10 to the power minus 3 plus 6 means oh, 63.6. Depending on what is the pi value we take, if we go more than 3.14, we'll get different values slightly here, but anyway, approximately it will be something like this. And then 10 to the power 6 minus 3 means 3 ampere per meter square. This is the current density we have calculated. Current density is done, charge density is done, value of charge we know. So now we are ready to calculate the drift velocity. I just need slide for the final step. Okay. So our final step is to calculate drift velocity, which will be current density upon NE. Current density upon this. Now current density we calculated, that was 63.694. 63.694 divided by the charge density was 8.5 10 to the power 28, 0.5 10 to the power 28. And this I forgot, 10 to the power 3. 10 to the power 3. And then charge of electron, which is 1.6 10 to the power minus 19. Yes. Okay. When I will calculate all of this, I will get 8.5 times 1.6 is 13.6. 694 divided by 4.68. 4.68 multiplied by 10 to the power 3 minus 28 plus 19. And the unit will be meter per second for this drift velocity, right? This will be 4.68 and 3 plus 19, 23, 5, 10 to the power, 10 to the power minus 28 plus 19. It was some mistake. I don't see 3. I think I did some mistake here. This would be 3.1 3.694. IMM. This will also correct. I think there is some mistake in power. I'm not able to understand exactly. This should be, wait, I'm getting 10 to the power minus 6 meter per second. I think there's somewhere some small mistake has happened for calculation. I'm not sure where. Let me check. I think I made a mistake here. So when I do this, 5, this is okay. And when I do 1, okay, so I did a mistake here. It should be this. This should be 0.31847 and then divided by 0.05, I will get I will get 6.3694. Okay, this was a mistake I did. And then this will also be 6.3694. Okay, and when I'll do that calculation, I will get this correctly now. 6.3694 divided by 8.5 divided by 1.6, it will be 0.468 and 0.468, and then I'll write 4.68 10 to the power minus 7 meter per second. Okay, so because of this one place, so please be extra careful. And then I think we have got the correct answer. 4.68 10 to the power 7 is the correct answer. Okay, so the next question is a copper wire. Okay, I don't know, I think this is some sort of mistake because it's the same question. Okay, anyway, yeah, it's the same question, so just it's the same. This is the correct answer, 4.68. So next question is, let's move on to next question. Next question is, we in copper, number of free electrons per unit volume, that is this electron density or charge density is given 8.5 10 to the power 28 per meter cube. This value is given, meter cube, and its conductivity is 6 times 10 to the power 7 per ohm per meter. This is the conductivity. Calculate the relaxation time of electron when electronic mass and charge. Mass is 9.1 10 to the power minus 31 kgs. This value we can remember also. Sometimes it's given, sometimes it's not given, but these are standard values we can remember, like the charge of electron, like we did earlier. So yeah, the charge of electron here it's given, but you remember in last question it was not given. So these are some standard values we should better remember. So charge of electron, either we use this symbol or we use small e. So charge of electron is 1.6 10 to the power minus 19 coulomb. So these are values given and we have to find out relaxation time. So in the lecture you must have seen what is the relation between relaxation time and the velocity and these parameters, conductivity. So conductivity depends on the charge density, the charge on electron, relaxation time and mass of electron by this relation. Okay, and here we need to find out the relaxation time, means it will be conductivity times mass divided by n and e square. So we'll put in the formula and find out. So the relaxation time is, as we saw, is sigma m and n e square. Now conductivity is given 6 times 10 to the power 7, 6 times 10 to the power 7, and mass of electron we know is 9.1 times 10 to the power minus 31. Charge density is given 8.5 times 10 to the power 28, 8.5 times 10 to the power 28, and charge of electron 1.6 times 10 to the power minus 19 coulomb. Square of this. Okay, when we calculate this, is 6 multiplied by 9.1 divided by 8.5 divided by 1.6 times 1.6. Answer will be 2.50919, and the powers will be 10 to the power minus 31. This will go in the numerator and become minus 28. This will be 10 to the power minus 38 because square is there, and when it will go to the numerator it will be plus 38. So the resultant here the final answer will be 10 to the power minus 31 minus 28 plus 38. This will be minus 31 minus 28 plus 38. So it will be minus 21, and since it's relaxation time, it will be in second. So the answer, did we do some problem here? No, everything is fine. 38 only. Oh, sorry. This is 10 to the power minus 19 means its square will be, wait, 19 times 2. Yeah, that is correct. It is 38 and it is 28. This is 31. I missed this. Sorry, I'm very sorry. Plus 7. So this will be 2.50919, and 7 minus 21 will be 10 to the power minus 14 seconds. So this will be the correct answer, 2.5, I think. Oh, sorry. So C is the correct answer. Okay, next question. Assuming that each atom of copper contributes one free electron, again because it's a monovalent, so every atom is contributing only one free electron. So calculate the drift velocity of free electron in copper conductor, where the conductor has cross-sectional area of 10 to the power minus 4 meter square and is carrying a current of 200 ampere. Okay, we have to calculate drift velocity. Now we know we can use this formula. Drift velocity we need to calculate. Current density we will calculate because we have current and we have area. Number density we need to calculate because charge of electron anyway we know. This is known. Only unknown thing to calculate this is number density. And here we are talking about copper. That means every atom gives one electron. And now the material is how we will calculate number density, we will see. So here we have been given density of copper, its atomic weight and Avogadro number. By seeing these given values, we should our mind should immediately go back to the problems we were doing when we were talking about density of unit cells, crystals. We had seen the formula that density of unit crystals was given by number of atoms and then atomic weight of that element divided by volume and Avogadro number. This was the formula we were using. Here density is given, volume, atomic weight is given, this is given, and volume we don't need because what they have given is per unit volume. Okay, wait, we'll see this and then okay. So using this formula, what we see is this formula is fine, this we know. Now if I calculate number of atoms per meter cube, then that means I don't need to worry about the volume. Okay, so what I'm calculating is this number of atoms per unit volume. So it will be density times Avogadro number divided by atomic weight. So I'm calculating number of atoms per unit volume because why? Because the charge density, this is number of electrons per unit volume. So if they anyway we need to calculate it per unit volume. So in this formula also we don't need to worry and actually use the volume here. We can just calculate this because that is what we need. So this is the formula. Then density is given, which is 8.94 times times 10 to the power 3 kg per meter cube. Avogadro's number is 6.02 times 10 to the power 23. Usually, although we use 6.023, but it's always good, whatever the value is given, we should stick with that so that our answer comes from the given options. So usually we used to take 6.023 times 10 to the power 23, but here if it's given up to only 2 decimal digit, then it's better to use this, and this is 23. Okay, divided by atomic weight. Atomic weight is 63.5. 63.5. When we will calculate this, it will be 8.94 times 6.02 divided by 63.5. Answer will be 0.84754 multiplied by 10 to the power 3, and we have 23 means 10 to the power 26. So number density will be 0.847 754 10 to the power 20 26 per meter cube. And all the units were okay, kg per meter cube, right? Everything is fine. Okay. Then now each atom contributes. Okay, there is one thing we need to focus here. Whenever we define atomic weight and we say it is 63.5, what it means is, whenever we say atomic weight, here like 63.5 atomic mass unit, or we just don't say anything, or it means 63.5 gram per mole. Sorry, gram per mole. Oh god, let me write here, gram per mole. Atomic weight, we sometimes don't put any unit, sometimes we put U, sometimes we put atomic mass unit AMU. Otherwise, we clearly write 63.5 gram per mole. Okay. So here atomic weight is in gram per mole. Okay. And we know 1 mole has 6.02 times 10 to the power 23 atoms. Everything else here, this is in density is in kg per meter cube. This is in kg per meter cube. So I need to convert this also in kg. So of course this is okay. This is in gram per mole. So that means 1 mole has 6.02 into 10 to the power 23 atoms. But this is in gram per mole. Because when nothing is written, it is understood it's in gram per mole. So I need to convert this into kg. And when I convert gram into kg, it will be 10 to the power 10 to the power minus 10 to the power minus 3. Okay, and when I do that, get correct, 63.5 gram per mole, 10 to the power minus 3. The final answer will be, after the adjustment, final answer will be 8.475 10 to the power 20, because this will become minus 3, 23.4. Yeah, because this is a minus 3, it will go on the numerator, it will become plus 3. The total will be 23, 24, 25, 26, 27, 28, 29. This will be 10 to the power 29. So these unit conversion are very critical. Even if we are applying the correct formula, our final answer will not come correct if we are somehow missed to do these unit conversion. Okay, so pay extra attention to these details. This will be this, and when I will take this decimal after 1, then it will be 10 to the power 28 per meter cube. Okay, so our power would have come completely different if this detail we would have missed. So this is number density, correct? And now we have everything. Now to calculate current density, current per unit area, that is this area is given. So 200 divided by 10 to the power minus 4 ampere per meter square. So our drift velocity will be current density divided by NE. Current density divided by charge density and charge of current. This will be 200 times 10 to the power 4, right? This will be 10 to the power 4 when it will come numerator. And number density is 8.475 times 10 to the power 28 per meter cube. And charge of electron is 1.6 times 10 to the power minus 19 coulomb. When I will calculate this, 200 divided by 8.475 divided by 1.6, it will be 14.74926, and the powers will be 10 to the power 4, and this will be minus 28 and plus 19. So this will be 4 minus 28 plus 19. That means 14.74. I just keep it to 3 decimal digits. So this will be 3 times 10 to the power minus 5 meter per second. Okay, and answer here. Oh, so answer here is I need to move the decimal point. The answer is correct, but we just need to shift the decimal point, and then it will be 1.4743 times 10 to the power minus 4 meter per second. And so this answer is matching the option A. A is the correct answer. Next question. How much time we have left? Yeah, we have time. So next question is estimate classically the relaxation time tau of electrons in copper. Again we have copper when its resistivity, resistivity is given, which is 1.69 times 10 to the power minus 8 ohm meter. Okay, and the concentration of free electron in copper is per meter cube, means number density or charge density of electrons is given, and we know copper is monovalent, means one atom contributes only one electron. So number of electrons per unit volume will be 8.5 10 to the power 28 per meter cube. And what we have to find out is relaxation time. And we know what relation we can use is relaxation time is given by mass of electron and divided by number density, charge of electron, and resistivity. And when we put all the values like 9.1, 10 to the power minus 31, see, that's why I was saying we should remember these standard values, because now here they have not given the charge value and the mass of electron. So these are some value we should remember, because if you will be taking exam for this course in the online exam, maybe these constants could be given or may not be given. So you should better remember. Divided by number density is 8.5 times 10 to the power 28, and this is everything is in SI units, so it's okay. Charge of current, charge of electron 1.6 10 to the power minus 19, and resistivity is 1.69 times 10 to the power minus 8. When I will do the calculation, it will be 9.1 divided by 8.5 divided by 1.6. Okay. 0. Okay, this is square, right? So the correct answer will be 2.47 and all the power 10 to the minus 31 minus 28 plus 28, no, plus 38 and plus 8. So our answer final is 2.47 times 10 to the power minus 14 seconds. So this is the correct answer. Next question. Estimate classically the mean free path of electron. Okay, we have to calculate mean free path of electron in copper at temperature 20 degrees centigrade. 20 degrees centigrade. This we need to calculate. Relaxation time of electrons is given, which is 2.5 10 to the power minus 14 seconds. Boltzmann constant value is given. Now we need to calculate relaxation time. So if you recall the formula, relaxation time is the distance covered, which is mean free path, divided by the velocity. RMS, root mean square velocity. So this here we have this, we will calculate VRMS and then we will get our mean free path. So to calculate mean free path, it will be tau, that is relaxation times, multiplied by RMS velocity. So we need to find out, relaxation time is given, we need to find out RMS velocity, and from Maxwell-Boltzmann model, we know that we can consider free electron like a gas, and the RMS velocity is given by this expression, which is same as what we get for gaseous particles. This is how RMS is given for free electron gas model. Okay, so from here we can calculate 3 times the Boltzmann constant is 1.38 times 10 to the power minus 23 joule per Kelvin divided by mass of electron, which is 9.1 times 10 to the power minus 31 kg. And when we will calculate this, this temperature also is there, and temperature in calculation we should always convert it into Kelvin. So that means 273 plus 20 degrees centigrade is equal to 293 Kelvin. Okay, that means multiplication 293. When we will do this calculation, we will get instead of calculating here, let's directly go to and put in the formula lambda. So as you know, lambda is relaxation times multiplied by VRMS, and VRMS we just now calculated 3 kBT by N. So this will be relaxation time value is 2.5 times 10 to the power minus 14. 2.5 times 10 to the power minus 14 multiplied by this whole expression 3 times 1.38. 1.38 times 10 to the power minus 23 times 293 Kelvin divided by the mass of electron, which is 9.1 times 10 to the power minus 31. When we will do this calculation, we will get, we have to multiply all this and take its square root. 1.38 times 293 divided by 9.1, it's 133, and 133, and the powers will be 10 to the power minus 23 plus 31. So 31 minus 23 is 10 to the power 8, and square root of 133 will be 11.5. This is there still. Okay, and this will be 11.5 multiplied by 10 to the power 10 to the power 8, square root of that. Mm, that will be 2 root 2. Yes, 2 root. Oh, what am I doing? Sorry, sorry. 10 to the power 8. We need to make it 10 to the power 9. It's 13.3. Square root of 13.3 will be 3.646. 646 times 10 to the power 3. And then we have 2.5, 10 to the power minus 14. So the final answer will be 2.88, and this will be 10 to the power minus 9 meter. That is 2.88 nanometer. The answer is 2.88 nanometer. Okay. Okay, so next question is, yeah, it's now on wave function, because we had seen that when we put when we talk about metal, so we just now discussed that there is iron core, I mean the core of the atom, positive, and then electron are flowing around, but they cannot escape out at room temperature. When they have a lot of energy, then they can break the attractive force and come out, but until then they'll just roam around freely here, but they cannot go out. So it's something as similar as potential box problem, where the electron can be inside, but outside the potential is infinite, so it cannot go outside. And there, when we apply quantum mechanics and find out the wave function for the particle and energy of the particle, so those concepts were also discussed in the lectures. You can go through there, and this question is based on that. So the question is, the question is wave function of electron in 1D potential box, something like this, of dimension A, that the box dimension is A, is given by this wave function. Evaluate A by normalizing the wave function to unity. So we know that wave function is normalized. The normalization constant, I mean, when we normalize means when we take its inner product, we get 1. Okay, so normalizing the wave function to unity, we can find out this constant. Let's see how. So this is the normalization condition, and there is dx here, and the x goes from 0 to infinity, because the particle can move from 0 to, this is I mean, this is just in general normalization condition. Here it can go from 0 to A. The particle can move from 0 to A. So when we take this wave function is A sine n pi by A x. This is wave function. And then we'll take psi star, because this is just a number, so it will be same, and this will be same. There is no imaginary thing which will change its sign, so everything will remain same. And when we'll take their product, means their multiplication, I'll get a square sine square n pi by a x, and the integration will be from 0 to a dx. Okay, and n we have to equate it to 1. When we'll do that, we'll see a square, I can just take out of the integral because it's a constant. So this will be a square and sine square n pi by a multiplied by x dx, and we can equate it to 1. So sine square, and of course the limit goes from 0 to a. Now we need to simplify this so that we can integrate. So we can use one trigonometric identity which tells us that cos 2 theta is equal to 1 minus 2 sine square theta. Okay, when in terms of sine square theta, it will be cos 2 theta minus 1 divided by, wait, no, sorry, this will come to positive side, then it will be 1 minus cos 2 theta divided by 2. Okay, so this, when we apply this trigonometric identity here, we see this is sine square and this whole thing is theta. So this expression will become, a square was outside already, this is integration goes from 0 to a, and instead of sine square we will write this. So it will be 1 minus cos 2, and the theta here is this n pi by a multiplied by x. N pi by a multiplied by x dx is equal to 1. So when we take integration now, oh sorry, this 1 by 2 is there, 1 by 2 is there. Okay, so this is also constant, I can take it out. So it will be a square by 2, and this integration I can split 0 to a, this 1 dx, and minus cos 2 n pi by a x dx, this is 0 to a. So when I will integrate this will be x and it will become a, and minus 0. A square by 2 we have outside, and this is a, and then this will be cos 2. The integration of cos is sine 2n pi by a, and we have x also, and then it will be this has to go from the values we need to put from 0 to a, and then we have this factor will go in multiplication, and actually it's division, it will be divided by n pi by a, actually 2n pi by a, and then we have to put 0 to a. When we'll further solve this, we'll get a square by 2, and a is there, right, this a is there, then this will be, I can take it at the front and it will become a over 2n pi. There is minus sign, and this is a over 2n pi. And here what will happen is, when I will put a here, okay, then a will be cancelled and I will be, let's see, so here sine 2n pi by a, and I have x, right? So when I will put, I have to put a here, then it will be, sorry, this is pi, this I'll put a, then a cancel, 2n pi minus sine, then next time I have to put 0 here. I hope you remember how to do integration. This will be sine 2n pi 0, right? So we see this is 0, sine 0 is 0, this is 2n pi. Now whatever will the value of n will be some integer, right? We know that sine 0 is 0, sine 180 is 0, so whatever be the value, this is 0, this is pi, this is 2 pi, then this is 3 pi, then this is 4 pi, right? This pi by 2, this is 0, this is pi, and then this becomes 2 pi. Then if we'll go further, this will be 3 pi, this will be 4 pi. So whatever be the value of n here, the sign will always be 0, because it will either be lying here or here. That means even this will be 0. This anyway is 0 because sine 0 is 0. This will also become 0. That means only I will be left with this. So a square by 2a, and this all thing is minus 0, and when we equate it to 1, then I needed to find out a value of a, right? So it will be 2 divided by a, and a will be under root 2 by a. So this is the value of this constant a, which is root 2 by a. So this is the correct answer, option C. And this is how we normalize and put the normalization constant. Okay, we need to use some trigonometric identity to make our life easier actually. Okay, so next question is, in a 1D potential box of length L, this time they are calling, instead of A, they are calling it L, maximum wavelength that an electron can have. Maximum wavelength that the electron can have. So for this we need to take help of some relations, like we know uh, energy of electron in potential box, the expression is given by, depending on which n we are talking about, energy is given by n square h square divided by 8 ml square, where L is the length of this potential box. Now we also know the relation between energy and momentum, which is this. Okay. Now from de Broglie wavelength relation, we know lambda is h over mv. This is de Broglie wavelength relation. That means this is h over mass times velocity is momentum. Using substituting, let me write it in. So it will be h over lambda. Now putting this here, I will get h square divided by 2m lambda square. Okay. In that case, the energy become h square over 2 lambda square. Okay. Because we don't. Oh, let me just do this. Okay, so now when we equate these two expressions, because this is also one way from which we get energy of the particle, and this is another way, another expression for energy of particle. When we equate these two equations, we get n square h square divided by 8ml square and h square divided by 2m lambda square. Because we had to find out wavelength and we are given potential box, so we use this energy expression and we derive this energy expression in terms of wavelength. So when we equate these two, we see these cancellations, mass cancel, this will be 4, so we will get n square divided by 4l square is equal to 1 over lambda square. And we, let me just get the expression. So this was n square divided by 4l square is equal to 1 over lambda square. That means lambda square will be 4l square divided by n square. When I'll take square root on both sides, I'll get lambda is equal to 2l divided by n. We have to find out the maximum wavelength that electron can have in this 1D potential box. The lambda will be maximum, length is fixed, so only way we can make it maximum is when n is minimum, and the minimum value of n can be 1. So that means the maximum wavelength is 2L. Okay. So for this potential box, the maximum wavelength can be 2L. So D is the correct answer. Okay. Next question. Calculate the energy difference between the ground state energy, okay, the ground state energy and the first excited state. Energy for free electron in 3D potential box. So we have potential box, but this time it's 3D. So we have X component, Y component and Z component in a box of 1 by 1 by 1 centimeter cube. So when we were talking in 1D, we were saying we have some L, but here we are talking about 3D box, 3D potential box. So instead of one dimension, we are telling all XYZ dimension. So it's 1 by 1 by 1 centimeter cube potential box. And Planck constant value is given. And we have to find out ground state energy and first excited state energy, the difference. So for 3D potential box, the energy expression Okay, we have nx, ny, nz because we have 3, it's 3D, and the value is given by h bar square pi square divided by 2m square. Either h or h bar you can write. I hope you know h bar is reduced Planck constant and it is actually h over 2 pi. So either you can write in terms of h or you can write in terms of h bar. Both are correct. Okay. In case if you write in terms of, okay, first let me complete the formula, and the expression will be nx square by a square, like a, b, c, I'm taking the 3 dimension, and ny square by b square and nz square by c square. This is the expression for energy of particle when it is in nx, ny, nz state. So here it's given the dimension is 1, 1, 1, means this a, b, c will be 1 square, 1 square, 1 square. We have to find out the energy of ground state. Energy of ground state will be when the particle will be in 1, 1, 1 state, means nx will be 1, ny will be 1, nz will be 1, because the minimum value of n can be 1. It cannot be 0. It cannot go negative. It is 1. So the minimum, the ground state will be 1, 1, 1, and the energy corresponding to that will be h bar square pi square divided by 2m square, and here it will be, because 1, 1, 1, and the denominator is also, I mean 1 square of 1 is 1, 1 by 1 plus 1 by 1 plus 1 by 1 means this is 1 plus 1 plus 1 means 3. So this is 3 times h bar square pi square divided by 2m square. This is the energy of ground state. Now let's see energy of first excited state. So the ground state was 1, 1, 1. Okay, the excited, this was ground state. Now first excited state, it can be 2, 1, 1 or 1, 2, 1 or 1, 1, 2. Okay, this will be excited state, but either it could be this or this or this. These all three will have same energy, and that's why they are called degenerate, because these three different states have same energy. When we will calculate, we will see all these three will give same energy value. The first excited state, we can consider any of them. Let's see, if we consider as I said, all these will be same, and the value, like if I put this, then I'll see what was the formula, h bar square pi square, h bar square pi square divided by 2m square, because all three have same value, so I'll just put this. So nx square means 4 divided by 1 plus 1 divided by 1 plus 1 divided by 1, because all three have same energy, so either you can take this or this or this. I'm taking this here. So this will be 4 plus 1 plus 1 means 6. So this will be 6 h bar square pi square divided by 2m square. Now the difference in the energy, first excited state energy, excited state minus ground state. Excited state is this. Ground state has 3 h bar square pi square divided by 2m square. When we differentiate, when we'll subtract, we'll get 3 h bar square pi square divided by 2m square. Okay, so this is the formula we got. Now we need to put these values and find out in definite this. I need one. So difference in energy, 3 h bar square. H bar I told is h over 2 pi, and h bar square means square of this, and because h is given, h bar, if they would have given h bar, we can use it directly. Pi square divided by 2m square. No, sorry. Yeah, pi square divided by 2m square. And pi square divided by 2m square. So this will be 3h square pi square divided by 4 pi square 2m square. Pi square gone, and it will be 3h square divided by 8m square. When we substitute the values 3 times, what is this? 6.6 10 to the power minus 34. 6.6 10 to the power minus 34 joule second, and square of it divided by 8 times mass of particle is electron. Yes. So mass will be 9.1 times 10 to the power minus 31 and square of that also. And when we will do this calculation, we will see the answer is 1.795 times 10 to the power minus 33 joule. So the energy difference is this, and the correct answer is option A. Okay. One more question. In a 1D solid of interatomic separation 2 angstrom, interatomic separation means this lattice constant is 2 angstrom, and the critical or minimum momentum value for which Bragg reflection takes place. Okay, we are talking about Bragg reflection, means this comes. We are talking about interatomic separation, means this is our I think they meant interplanar spacing, because in that case otherwise they have not given d value and they are not telling about if it's cubic or not. I think they meant interplanar spacing. So we can write it like this. Okay. So now we know the relation between momentum and lambda, and we have to find out when the Bragg reflection happens for the minimum momentum. Minimum momentum means maximum lambda, because they are inversely proportional. So we have to find out for minimum momentum means the lambda will be maximum. So lambda here is 2a sine theta divided by n, and lambda will be maximum when this will be minimum, and minimum value of n, minimum order can be 1. So lambda will be 2a sine theta, and also it will be maximum when this will be minimum and denominator will be minimum, which can be 1, and numerator will be maximum. 2 and a is constant. Sine theta maximum value can be 1. So this also will be 1. So lambda is equal to 2a is the maximum lambda possible, and since lambda is maximum means momentum is minimum. Okay, from this relation. And okay, lambda maximum means momentum minimum, and the value of momentum will be h over, because lambda is 2a, so this will be h over 2a. Now we need to calculate this value. E minimum will be h over 2a. Value of h is 6.64. 6.64 times 10 to the power minus 34 joule second divided by 2 times, and the value of a is 2 angstrom, means 10 to the power minus 10 meters. When I will calculate, I will get 6.64 divided by 4, 1.66, and the power 10 to the power minus 24 kg meter per second is the momentum. The correct answer is option D. Okay, so these were questions and the topics that we discussed. We mainly discussed about uh, yeah, Brilliant zone, how to draw them, the first zone, second zone, and then we discussed what are the various factors on which the XRD peak intensity depends, like structure factor and multiplicity. And then we switched to discussing electrical properties of solids like current density, density of states, and then these were the questions we discussed. So if there are no more questions, we'll end today's session.